Great. Yeah, so hi everyone, and thanks for joining in person as well. Yeah, so I will talk about hexagonal sliding puzzles, and in general, sliding puzzles I think are a set of puzzles that mathematicians loved since a couple of 100 years ago. And yeah, hexagonal sliding puzzles, I'm sure that no one has seen them before because actually it's the first time that they're studied, but perhaps you have already thought about the idea of why there are not hexagonal sliding puzzles if you have played other kind of sliding puzzles. Yeah, please stop me anytime. And if there are questions, yeah. Is it working?
Yes, I just have to be sure that the screen is visible.
Yep. Okay. So this is the most famous sliding puzzle, and it is the 15th puzzle. And so the task of the puzzle is you have the left configuration where you have all the numbers in here ordered up to 13, and you have 15 and 14 exchange. And then the task is to move one tile at a time to the empty space. And you can do this as many times as you want, but the goal is to get the right hand side configuration. So yeah, this is the task. And I don't know if some of you know it, but in the 80s, this puzzle just drove crazy a lot of people, and then of course mathematicians jump in. And so in 1879, just 1 year after the puzzle was around, then Johnson proved that the 15th puzzle is unsolvable. And is this particular puzzle? Yeah. He showed a little bit more, as I'm gonna say after, but in particular, he showed that the 15th puzzle is unsolvable. And there were actually two parts to this paper. And there is another author that wrote the second part, but the first part of the paper is that has that the 15th puzzle in particular is unsolvable. And I think most people know about the 15th puzzle and that it is an impossible puzzle, but I don't think that a lot of people know how the proof was splitted and why. So yeah, Johnson wrote the part that shows that the 15th puzzle is unsolvable. And by the way, it was in American Journal of Mathematics published, and the editors like wrote 2 to 3 paragraphs saying, okay, it might seem that this is a very, very serious journal of mathematics, and why are we publishing something about a puzzle? But then they mentioned, okay, this has very interesting proofs that are actually problems that are addressed by other mathematicians and that actually lead to very interesting mathematics. And another example that they gave in this apology for publishing this paper actually had very very good examples of what we know as recreational mathematics and why it is why it actually developed interesting mathematics. Okay, so if someone wants to go and read the apology, please do. And so the two parts of this paper, when I was reading it, with my collaborator, we realized that actually these two parts of the paper show a very interesting, two different very interesting properties of sliding puzzles, or this kind of mechanical toys. And so we split it into weak parity property and strong parity property. So the weak parity property says, if you fix the placement of the hole or the tile that is missing, and then starting from any configuration, what he showed is that it is impossible to reach any other configuration that is obtained by applying a not permutation to the labels. So if we go back, we see that we actually need to permute 15 and 14. So this is one permutation, so it is a not permutation, so it is not possible. And it has to do to look at the parity of the permutation. And yeah, the proof is nice, but is right now for us that we're like so acquainted with group theory, it is really not amazing now, but it was at the time. Okay, so yeah, so you need to exchange 15 and 14. So this is only one permutation. So it is impossible, but he proved even stronger thing, that you actually cannot attain any configuration that will require you to an odd number of permutations. So, and this is the weak parity property, okay? And then the second part of the paper answers the question, well, then which configurations are attainable, okay? I cannot attain the ones that are at odd permutations, but this doesn't answer you which ones you can attain. And so the second part is the strong parity property, and it shows that all configurations that can be obtained by an even permutation of the tiles are attainable. Yeah, so what we define as a strong parity property is you cannot attain the ones that are odd, but on top of that, you can attain all the ones that are even. Yeah, so these two are the two parts of the paper that were very interesting to see, like separated as two different properties. And okay, so now the puzzles that we are interested in analyzing are not longer like coming from the square tile. Perhaps you can, yeah, zoom. Now what we do is we say, okay, let's explore what is happening with the hexagonal sliding puzzles. And so, by the way, this is just a commercial. You can download the OBGs or the FBX to 3D print this for free in your 3D printer. Yeah, Henry Segerman did the nice design on the numbers also. If you have heard of Henry Segerman, who is like very famous of using 3D printing for in mathematics. Okay, so yeah, now we have hexagonal sliding puzzles, and it's even interesting when we have this configuration of the board and only one tile. So let me put two tiles because when we buy the 15 puzzle, we have actually only one space empty. But then if you try to move them, they are completely stuck. So at least for this board, I do need to have two tiles that are not there. And that allows us to move this tile to any of the other two spaces. Yeah. So now the model that we're gonna use is the puzzle graph. And let's do the puzzle graph for this simple example with observation, very important observation. No, it's okay. With a very important observation that that we do need two tiles to be missing to actually move them. So this is the picture of needing two tiles. And this is a geometric imposition of the puzzle, right? If you change your tessellation or your sliding puzzle, you might have different positions. So let's draw one vertex for each one of the possible positions, and the positions have to be actual positions of the tiling right now for the puzzle graph. I'm gonna say something about the configuration space that you actually have when you allow continuous movement. But right now, the puzzle graph, which is the discrete structure, so you put a vertex for each one of the possible positions of the cells. In this case, A could be in any of the three. And you use this here, you do it if they can reach or not, it doesn't matter. And then you connect two if you can go from one to another one. So in this case, we get a triangle because you actually can move A in this way. So this is the puzzle graph. And in general, when we have a board with H holes or H tiles removed, not topological holes here. So this is a very different talk from yesterday, just really tiles removed. Then the puzzle graph has a vertex for each one of the possible placements of the tiles and edges between two vertices or two different configurations if it is possible to go from one configuration to the other one by sliding one tile into a hole. Okay, so we did the simplest one that we could do. So let's do the puzzle graph for this one. Yep. So I think now I can use the whiteboard. Yeah. So let's do it together. So I'm gonna put it here and or here, doesn't matter. Yeah. So let's just increase the board by one tile in this way. And let's see what happens with the graph. Now, the graph when the board has three hexagons and only one tile, we already saw that it is connected. So there's only one component and three vertices. So now let's see what happens here. And the important thing to do the graph is to know all possible movements that we can do. This is not the puzzle graph. So this is not the puzzle graph. But it's going to allow us to build the puzzle graph. So what I'm going to do is, for helping us, I'm going to connect if you can move actually the tile from one position to another one. So here you can convince yourself that this is the way that you can move the tiles. So once you have a tile here, you can go up or you can go down. So this is this 2, and it is symmetric with respect to any other vertex. Now, let's label them. So let's say I have okay. So now we know how to represent this, and let's see if we can say where are the tiles. So if we have tile A and tile B here, and it's important that we do this example because it will allow us to first know if this board has any of the properties that we said, like the weak or the strong parity properties, and just to be on common scenarios. So, okay, so what I could do from this configuration. So we know that we need to have two empty tiles to be able to move the tile. So B actually cannot move here, right? So we can go for B is stuck here, but A could move here, or B is still stuck here and A moves here, right? And then from here, now B gets freedom, and now B can actually go with A stuck here, B could go here, or with A stuck there, B could go there. And there is nothing else we can do. I don't know if you agree, but I will let 2 seconds for you to agree on that. Yes. So you only have one empty space, and so this configuration will be like this. And then the tile is blocked, right? You need to have 2 spaces, and this is the main difference with the squares puzzle, where you actually can move to any empty tile or cell, but here you need to have 2 that are neighboring you, and then you can decide where you go. So we agree that these are the only 5, no? Yeah. Okay. And guess what? If we interchange A and B, we get the same. So if we start, I'm gonna put it here. if we start instead with A and B like this, and we start with B and A like this, we will also get 5 elements, just permuting A and B. So we have 5 elements here, 5 elements here. So these are 10 elements, but how many positions could I actually generate here? 12. So what are the other 2 positions? There are ones you cannot move, right? So these two positions are the, what I will say are the block positions, or the ones that from the beginning cannot generate more than themselves in the puzzle graph as the components. So we have 5, 5, and 2. And so question, does this has the weak parity property? The weak parity property, and I can, yeah, perhaps I can go back to the properties. Or if you want to answer the strong parity property directly, it's okay. But you cannot attain any odd permutation. So for example, for here to here, what you actually need to do is only permute the empty with A, right? And it's the same here. And these are isolated. So the weak parity property tells you that you can not obtain the ones that are at odd permutations of the cells once you fix the whole. And then we do have that. And the only thing is that these 2 guys are completely isolated. But if we take if we model out the ones that are stuck from the beginning, that means when you have all the holes isolated, it doesn't matter how many tiles you remove. If these are not touching each other, you will not be able to move the cells. Okay, so in this sense, this puzzle has the same property as the 15. You have 2 giant components, and they are actually parity is what is governing which elements are in each one of the components, and you have 2 isolated vertices. So this is new, like having isolated vertices is new, but it's coming from the fact that sometimes you have stuck like anytime that you have the holes isolated, you will have stuck configurations. So we're kind of going to ignore these configurations that are stuck from the beginning, and we're gonna look at what's happening to the components when you can actually move the tiles. Yep. So there is hope, right? Because this 2 by 2 is behaving as a 15 puzzle. You have 2 giant components, and that's it, and the isolated ones. Okay, so if we have hope, let's keep going. I will go back to there after. So what about this one in terms of solvability? Do you think that you can go from the configuration of the right, now with the intuition that we have, from the configuration on the right to the configuration on the left? Do you think that you could do it? Yeah, so I don't know, people in the audience can also guess or bet. Yeah, so I will go back to that. I will answer this question, but if someone wants to take a picture and start trying to solve it there, it's time to do it. But let me introduce a family of boards, because actually the family of boards that are studied in the square case are the n by n boards. But let me tell you that actually it doesn't matter, because it was already solved for general bipartite graphs. So that's why it's not even interesting to start talking about different boards there. Yeah, exactly. So So the family of boards that we're going to study is the analogous of the square one, and this is the analogous of the square one, is a parallelogram, right? So this is 2 by 2, this is 3 by 3, this is 4 by 4 on the hexagonal sliding puzzle. And then we have the family of the triangular ones, and you have, this is the first element, and then you have this element, right? And then you have this element. So these are the families that we are interested in actually characterizing what is happening with their puzzle graph. And then you can also study this beautiful, what we call the flower on the paper, the flower family. So the first flower will be only one hexagon, not interesting. And then you add all the cells that are neighbor at least at one edge. And then this is the analogous going from this to this. You add all the hexagons that are sharing at this one edge. And this is kind of a weird guy that you could think that is coming from here. Instead of 2 by 2, you go by 2 by n. Yeah. And so these are the boards that we analyze, but we actually also have a general theorem. So even a bit more to let you use your intuition, and then to get perhaps disappointed, I will let you guess which one of these families of boards will exhibit the same kind of properties that the n by n square sliding puzzles are exhibiting. So this is the parallelogram one, this is the triangular one, this is the flower, and this is the 2 by n. So you can start betting there. And I'm gonna put here, I'm gonna write here some notation that we are gonna use. Yeah. So let me also tell you that my collaborator in another paper, Hannah Alpert, we were at OSU, and she was studying the diameter of the puzzle graph, of the hexagonal puzzle graph, and then okay, she said, I'm going to study also this particular family, the diameter of the puzzle graph. But of course, you're going to ask, but wait, these graphs can be disconnected. But what she did was finding a number of cells that you can remove in such a way that you know that the puzzle graph is maximally connected. And maximally connected here, maximally connected means that all those positions that you can not do anything because the tiles that you're removing are isolated, you cannot move, remember? So this is only making this modulo the stock ones. So what she found is that for the parallelogram one, that is this family 2 by 2, 3 by 3, 4 by 4. She studied the asymptotics of the diameter of the puzzle graph once they are connected. So actually you cannot see even here for n bigger than 5. So this is 4 by 4. So the boards that I'm showing you here are not the ones that Hannah Alpert studied. Okay, because you actually need to start in the next element, 5 by 5, and you need to remove 6 pieces, okay, or at least, because then you can be sure that the graph is maximally connected, so that you can actually reach all possible configurations that do not have the holes isolated. So this is what she did in this paper. And then I remember perfectly, we were all having lunch and discussing about this, because I love sliding puzzles in general. And then I asked Hannah, why 6? Why you assume that you remove 6 tiles to be able to have one giant component on the puzzle graph? And then she said, I don't know, because it was easy to prove removing 6, and I'm doing asymptotics, so I don't care, right? And then I asked, okay, what is your intuition? Like, what happens if we only have like 2 of the tiles removed? Then it's not going to be connected. You can convince yourself very quickly, even in the 2 by 2, we already saw it. What about if I remove 3? If I remove 3 hexagons, what happens to the puzzle graph? Yeah, so even here, if I remove 3, I don't know, but anyways, if I remove 3 hexagons here, tiles, if I remove 3 tiles here, and so on and so forth, if I remove 4, 5, and 6 is 6 tight. And here I'm gonna let you also bet how many tiles you need to remove to have only one giant component, and what is happening when you start removing one at a time. So clearly, if you remove one more tile, you are gonna merge some components. So at least the number of components is actually decreasing, the ones that are not isolated again, until you have only one giant component and isolated vertices, right? But then when this happens, in this,
I see no decreasing. First, why should it be increasing?
no, it's decreasing. Like they're merging. So the number of big components is decreasing until you have only one. Yeah.
But are they really decreasing whenever you remove a tile?
Yeah, until you have only one giant component. Yeah, you can prove this because once you remove one tile, that triangle was not possible to have the permutations, but now you can have a permutation there. So yeah, this is always, the number of components is always decreasing, of non-trivial components is always decreasing as you start removing tiles. But right now we have no idea of the number of big components, but we know that once you have 6 tiles removed, because of what Hannah proved, once you have 6 tiles removed, then you have only one giant component and isolated vertices, right? But then, of course, this was a very natural question to bring up during that launch, and it ended up being almost 2 years research project. Yeah, so now everyone is writing down their bets, and I hope I'm not gonna be spoiling anyone's fun. So yeah, this is the board that I already feel the 2x2, right? So once you remove 0, well, everyone's stuck. 1, we saw you're stuck. 2, you have 2 giant components and the 2 isolated, each one with 5 elements. 3, you clearly have only one cell that you can move, so it becomes connected. So what's happening in the 3x3? At least I think you could play with that. Okay, so just to tell you a little bit of how this will go for the n/2. And here, actually, I think you could come up with your own proof, trying it a little bit. So 2/n is this guy. I need actual numbers, but actually it's not gonna matter. But yeah, and then if I ask you to build the analogous in the square grid, you're gonna be able to do it immediately. So let's say that I have removed 2 tiles and I have them in this configuration, because actually all the non-trivial components, and this is a nice exercise for an undergraduate, all the non-trivial components are gonna be isomorphic. So, but then if you start moving this one, so I move the 12, this is a 12, and I move it here, or I move it here. Okay, so let's say I move it here. Then I can move the 8 either here or either here. But no matter what I do, apparently I won't be able to jump the 12 with the 8. So I move the 12. I have 2 options for the 12. And then I have 2 options for the 8, but the 8 will always remain below the 12, no matter what I do. Yeah, because even if I go here, the 9 remains below than the 8 because it was below at the beginning. So it preserves the order as you go in the stair. So this 2/n is super boring, and it's not like keeping the properties of the 2x2 when you go to the 2/n, right? And if you force me to build you like a puzzle with squares that will resemble that. I don't know if people can see this. Yes, perfect. So it will be one long board with numbers 1, 2, 3, 4, 5, and then you can only place them up and down, right? So this is the analogous of the 2 by n, the 1 by n, okay? And so now we prove together very easily. Again, you can only go up or down in this stair, but you can never jump the tiles. And we have proved this theorem that the 2 by whatever it's bigger than, sorry, here, bigger than, well, actually it also works with 2 if you plug in numbers, has m times m2 minus the number of empty cells factorial components that are not trivial. Yeah, because the trivial ones are the ones that are going to have the holes isolated. We don't care about those. But and so here we see a very different behavior than the square, than what is happening with square sliding puzzles. Yep. So unless you have only one column. Okay, so this was easy to prove, all of us. Now I'm going to start spoiling all the questions that I did. So 3 by 3 with 2 holes. Each non-trivial connected component has 80 elements. So we run an algorithm here. We started from a configuration. We fix all the empty cells in a place. And then we start from a certain configuration. And then we just do the tree that you can reach. And then this is how we did it. And you can actually access the code and use it. So each non-trivial connected component has 80 elements. But how many components we have? Well, at least it has the weak parity property. So you cannot attain anything that is at odd permutations. That's nice, but it does not have the strong parity property. Okay, because you have more than 2 giant components. If you go with 3 holes, so we are in the 3 by 3, okay? So now we remove another tile. So each non-trivial connected component has 52,560 elements. It is maximally connected. You only have one component. So from having tons of components, you only have one component. So it doesn't have the strong parity property that the square sliding puzzle has, that you end up with 2 giant components before merging everything. Yeah. And what about n by n? Well, n by n, I still let you think. I'm going to solve it at the end. But actually, the 3 by 3 has all that we need, and you're going to see why. So the flower. So what do you think about the flower? If I remove 2 cells only, and if I ask you, for example, to go from this configuration that has 7 and 8 exchange, do you think you can solve it? No, we have here no. We have 2 no's here, and I guess the audience is also screaming no. So I was visiting a friend in Brussels, and they have like they shared the apartment with 3 more people, non-mathematicians, artists, and I let this to one of the artists, and half an hour after I came back, and this was the message that I got from the person: impossible. And then but I make amends with this person anyways. But so experimenting on humans, it's sometimes interesting. Yeah, it is impossible. So and just to uncover everything at once, this is what happens. If you remove 2 tiles, you have 24 components that are non-trivial, and the component size of each one is 60. If you go to 3 holes, you have 6 components still not connected. And this gets fun because you tell the person, okay, now I'm going to make it easier for you. I'm going to remove 1 more tile. And then you make them try the same puzzle, and then it is still not connected. Not maximally connected. And then with removing 4, you jump to only 1 component. So again, you don't have the strong parity property here, because the strong parity property asks you to have a certain amount of tiles that you remove, and you have two giant components. These giant components being characterized by if the permutation of the tiles is even or odd. So very different behavior from the square sliding puzzles. And I have 2 minutes. I'm gonna start running. Yeah. So then when in this family we have the first flower, right? And then what happens when we go to the next flower? So in the next flower, the question will be, do you think that we will have like tons of components before merging to only one component, or not? Let's see the next one. Well, actually, it has a strong parity property with two holes. So here we needed to wait to remove 4 tiles to get one giant component. And before that, we have 6 components. And here, if you have 2 tiles removed, you already have the same behavior as in the square grid with 1 tile removed. So flowers from this element of the sequence on will exhibit exactly the same behavior as the sliding puzzle. And this was nice, right? Because the n by n actually don't has this property, and we were a little bit worried that we will never find like a family of boards exhibiting the same strong parity property. Yeah. And just to tell you a little bit of how we proved using the proof of the 3x3, well, I'm going to explain you the theorem here. So what you do is if you prove it for a 3x3, then you can have a kind of it's okay. I can do this. Yep, when it's the same. What you can do is you start doing like a patching algorithm. What you do is you start moving the board that you already understand to generate other boards. And if the intersection of the patches or of the copies that you are taking to generate the bigger board have a nice number of intersecting cells, then you can extend whatever properties have the small board to the bigger boards. Okay, so here we know that if we remove 3, we get connected, and this is allowing us to say the same for bigger boards. And yes, it is not possible that in the bigger board you will get actually connected before, because then you can reduce it to this. And so this is the patching theorem, and this actually goes to any other board. So here again, you can start patching bigger flowers with this flower to generate it, and the intersection of the copies of the board, it's gonna have the nice properties that we proved that you need to actually allow you to say that the next flower is actually like yeah, it will have the same properties. And the same happens, as you can see, with the triangle. So we did this computationally, and then we used the patching theorem for the complete family of boards. Yeah, so basically the patching theorem allows us to do everything. And now if you're already thinking that, okay, what is actually differentiating the ones that are going to have the square, like the strong parity property that is similar to the n by n in the square case, where you have 2 giant components at some number of tiles removed. Well, these 2 don't have this property, and the flowers do, and things are going messy in the corners. So the flowers don't have this problem. And then what we did is we cut the corners of the triangles, and we defined trim triangles and trim n by n parallelograms, and we actually have the strong parity property. So apparently what is the obstruction that we are getting is on the corners of these boards, but we cannot prove yet that this is the only obstruction that you can get. At least for these boards, this was obstruction. Once we trim the corners, then we can actually assure the strong parity property. And yeah, good. Yeah, thanks. I have 2 minutes for questions, but I guess, yeah. Yeah, thanks.
I guess if anybody has any questions, feel free to either unmute yourself and speak, or you can also ask the question in the chat and I will see it. In the meantime, I actually have a small one.
Yeah.
So for the sliding square puzzle, like the 15 puzzle, what this parity property essentially means is that you're either in the alternating group or not.
Yeah,
right?
you
So
can.
there
Yeah.
is kind of some underlying group structure there that kind of the connected component, or at least one of them, corresponds to a subgroup
Yeah.
of the symmetric group.
Yeah.
Does a similar thing happen in this general?
Yes, and you can actually spot where is like this kind of substructures of groups happening. And for example, in the corners is where you're gonna have like elements that you cannot attain by these permutations. And this is why when we cut the corners, we kind of merge these components. So the answer is yes, and we give a characterization actually of that as well. So
like one connected component that corresponds to a subgroup.
To each one of the subgroups. Yeah, yeah, yeah. I mean, characterizing for any subboard of the hexagonal tessellation, I don't know. Right? I like we explored these particular boards with respect to understanding what's going on the on the components or the groups that are acting there. But like in general, I cannot tell you how to characterize what can happen in the hexagonal in subboards of the hexagonal tiling. Yeah.
Is there any question online? If not, I actually have the second one.
Yeah, yeah.
If you look at, you mentioned this in the beginning, if you look at the actual configuration space.
Yeah.
Things, right? So I think my intuition tells me that in the square puzzle, that should just be the same as the graph, right? Because you can have a one-dimensional.
So it's a non-trivial problem, and actually there is a recent paper by my PhD advisor et al., including my mentor right now, Uli Bauer, and I think Hannah Alpert is also in that paper, where they showed that when you have one tile removed and you look at the configuration space in the sense of continuous movement of the cells, you can deformation retract this cubical complex that they prove that is a cubical complex. You can deformation retract it to the puzzle graph with one hole.
But that's for the square things, right?
Yes. In the hexagonal case, I discussed it with Hannah, and we have counterexamples immediately. We have counterexamples even. Yes, that's a trivial counterexample. So yeah, the graph that you get is like a Y, and here you have a triangle. So this is contractible, and the triangle is not contractible. So, but it's more than that. It's like it is not only that this small case is going to be the pathogenous case. We have like tons of examples where you cannot actually deformation retract the configuration space that you're getting to the puzzle graph. Not even when you have these giant components, because we thought, okay, perhaps when you have these two giant components, when you have the strong parity property, but perhaps we can save it. Not for any amount of tiles removed, because perhaps it's messy, but then when we have exactly two giant components, we can do it, and no. So it gets more interesting, which was a good thing, because at the beginning we thought it's gonna be like you know, like, yeah, by the way, this also, this property between the configuration space and the puzzle graph still holds for this other, but no. So the answer.
Is there anything you can say? I guess something along the lines of that zero setting on the saying, or I mean something along those lines. Is there anything?
Modulo the isolated vertices. I'm not sure we can even say that yet. But yeah, we're working on trying to understand what's going on in the configuration space with these guys. Yeah, right now.
All right. Are there any other questions? One other local participant or online?
No?
Seems to be the case.
Yeah. So I guess go and print the puzzles if you want to have them for activities or just to play with them. So in the GitHub, you just go to the puzzle model zip1, you download it, and then you just 3D print them. Yeah, they're ready for 3D print. Okay, thanks.